Okay, so welcome everyone to today's webinar. Um, Today we will be presenting upcycling strategies of dairy byproducts and waste for value-added applications by Sergio Martinez Monteagudo. Dr. Martinez Monteagudo is an associate professor with an split appointment in the Department of Family and Consumer Sciences in Chemical and Materials Engineering at New Mexico State University. His position also supports the Center of Excellence in Sustainable Food and Agricultural Systems. Before joining NMSU, Dr. Sergio worked as an assistant professor at South Dakota State University, where he applied concepts of chemical kinetics to produce sweeteners from lactose. Throughout his career, um, Sergio has published 55 peer-reviewed scientific articles, 14 book chapters, 3 invention disclosures, and over 100 abstracts. Additionally, he has secured more than $6 million from 21 grants awarded by various agencies and private industry. Dr. Sergio has also served as a reviewer for research proposals from the United States, Canada, Mexico, Colombia, Chile, and the Netherlands. He holds a degree in chemical engineering and a master's degree in food science and technology from the Autonomous University of Chihuahua in 2005, and he has earned his PhD in bioresource and food engineering from the University of Alberta in Canada. He also has worked as a postdoctoral researcher in food safety engineering at the Ohio State University. Now, thank you again all for being here. Before we start, please remember to mute your microphone during this presentation. If you have questions through it, you can either write it on the chat so that you do not forget them at the end, or you can also ask them directly to our speaker at the end of his presentation. Thank you everybody for being here with us, and welcome, Professor. It is a nice pleasure to have you with us. Now the audience is yours.
Thank you. So just let me share my screen here. All right.
We have the presentation with the,
okay.
Yeah, there it is.
Now, let me choose a color here. All right. Firstly, I would like to thank the organizing committee for letting me present and talk about the research that I've been involved with over the past few years in relation to upcycling, value added, and there's a lot of terminology that is not really clear to me. So I use my research in a way to put the baseline to start talking about some of these concepts that are a little bit ambiguous, and through the presentation I'm going to cover some of them. So, but mainly gonna pay attention to 4 points. The first one, I'm going to start talking about the production consumption cycle, which is another word for the supply chain, and then how that concept can lead us to the famous circularity or biocircularity, which still I don't know what it means. And then I will link that one into the term of cycling. And then I'm going to present a few case studies on what it means to upcycling foods, which is very different from other fields. And I will close this presentation with some thoughts where I believe we're going with this topic. So let's start with the very basics. So the production consumption cycle. So here is an illustration of a typical from production. Any commodity you think about it, can be corn, milk, any commodity in general. So if we go in this direction, we can talk about the commodity. There are energy involved. There are, every time that is an agricultural field, there's going to be waste and byproducts. And that leads us to the production. Of course, this is a simplification, as a simplified diagram of how complex can be. And during the production, there's energy inputs, and there are output that usually comes in the form of waste or byproducts until it reaches the consumer consumes the products, and there is more waste. This simple diagram illustrates very well we can use as a starting points and illustrate very well where is in the energy and water needs, what are the technologies that we can improve, what are the main ways, the byproducts, the end products, and all that. But what is surprising about this, when I put it in a linear way, but these are not linear. So at every step, there is so many inputs and outputs that is hardly linear, and that idea, the linear production versus circular, is the part that it creates some confusion, at least to me. And regardless of how complex can be this product consumption cycle, there are three main characteristics. So they are optimized for high volume. Regardless of, think about any product, your favorite food product on the market is optimized to high volume, low cost, and it can reach every corner of the world. Now, by now, we saw it during the pandemic that that's not a good strategy. So they are fragile, vulnerable, and they are not equal. So those flaws becomes very, very evident during the pandemic. Then all of a sudden we start having a shortage for everything. So we have shortage for construction materials, all kind of shortage, just not materials itself, also skilled workers. So all that we witnesses into the during the pandemic, and then start to think about, well, maybe the way we produce services, goods is not the best way. We haven't done it yet. So that lead me to the concept of circularity. And then when we talk about circularity, so this is perhaps a better illustration that it goes to circularity. What I mean by that, we start here at the farm, we go to storage, processing, packaging, distribution, retail, consumer, and it goes back again. Okay, so what it means between that, there are terms that we can talk about, saying, well, we need to be more adaptable, flexible, resilient, and all those metrics or terminologies start to appear. And there are already some of them. And we can come up with some metrics about how sustainable we are or how circular we are in terms when we produce specific goods and services. And we can measure that through life cycle assessment, through a specific energy, carbon footprint, water usage, so on. So, and here's when it becomes a little bit complicated in my view. So if you start getting into the literature of those terms, it's very inconsistent, and the part that it's frustrating me a little bit is dichotomic words. What I mean by dichotomic words, you find very common in the literature: revolutionary versus evolutionary, linear versus circular, radical versus incremental, recycle versus upcycling, and so on and so on. So I did a simple exercise here, and that perhaps is my academic nature. So I randomly took some publications on the topic using the keywords like circular economy, upcycling, food supply chain, and I just copy and paste some of the conclusions and introduction. And of course, I use a word generator, one of those word cloud generators. Of course, I use the one that is for free. And to my surprise, there's so many different words to say the same thing or to convey the same message. We're using so many words and so many different definitions. And that is a problem. And that is a problem in my view, because we cannot even, as a scientist, we cannot even come up with some agreements how we're going to communicate to our citizens how we can improve their life, how can science can help in making more sustainable, circular, if we cannot even agree ourselves with the terminology. So that's one of the characteristics. And then if we go in a little bit more details about what it means by upcycling, which is apparently is a new tool in the toolbox. Upcycling has been there under different name for a long time, and it calls valorization in previous literature, and well, I'm talking about 15, 20 years ago. But essentially a good and a very simple definition is upgrade and reuse. So everything that you can upgrade and somehow reuse might fall into the definition of upcycling. And that is an essential tool if we're talking about circular economy or circular processing. When you have raw materials, you design it in such a way that when they are produced in retail, they can be consumed, repaired, collect, recycle, and it goes in circular motion perpetually, and everything works well. So upcycling is a tool that can help us to reach to that point. And let me give you some examples of upcycling in other fields. So, for instance, IKEA design these wooden stools in a way that when you are tired of that, where you don't want to sit anymore, when you somehow decided to change the fashion of your house, you turn it into a bike or you turn it into a sled like these ones. Those are designed in that way on purpose from the very beginning. So that is a very good example of upcycling. A material that is you don't have use anymore for that, you can turn into a bike. That's great. Coke launches the Second Life campaign, in which basically plastic bottles can have a second use, and you can use it, for instance, to create bubbles, filled with water or sand, and use it as dumbbells or crayons, many different ways. Heineken also redesigned their bottles. So in a way that you can, once you drink the beer, you can put it in different pieces like Lego pieces and start building, for instance, a kind of a nice little house like this and stuff like that. So those are really cool examples of upcycling materials and upcycling, especially packaging materials. Here at the university and at NMSU, they also have the sustainable or upcycling fashion runaway, in which the students of fashion and merchandise, they design clothing for using waste or products that have no value. So, but keep in mind here, the idea is upcycling in reuse. But what does it mean to apply this concept of upgrade in reuse into food products? That's when it started a little bit of the definition is started getting a little bit confusing, because even though there are already some associations that utilize that you can claim that it's upcycling food, like Upcycling Food Association, Food Revolution Network, so on. They already exist and they have their own guidelines how you can call it upcycling food. But for the purpose of this presentation, I will stay away from those definitions and I will focus more on the scientific side and go back to using the definition. So one of the unique papers that actually cover the definition of upcycling. In a very simple way, there are two ways to upcycling food products. And here is the first case. You can upcycling food products to alternative use. And I use the example of the food waste hierarchy. So essentially, we can identify the source of the waste, reduce hunger, feed animals, industrial uses, compost, but the last step should be landfilled. That should be our last step. Of course, at every stage, there are significant challenges in this, but the most preferred will be reduce the source of waste, and the least preferred will be the landfill. That is one way to upcycling food products. And then there are already many examples about it. Whey proteins, for instance. A few years ago, cheese whey was considered a waste, and now with the filtration, with the right technology, you can separate the proteins, the whey proteins, and dry it, and now it becomes a very valuable commodity. The second definition, or the second group, we can talk about through a novel use, or very different use that was not really alternative, and that is essentially moving up into this food waste illustration when you go to different stages here, and the idea here is to moving up to having a different use for that material. Now, what does it mean in practical applications when we're talking about upcycling foods? So let's think about, again, let's go back into the very simplified production consumption cycle, in which we have the farm. In the farm, we're going to have spoiled products. They're going to be waste. We're going to have biomass. And then after that, whatever we can harvest it and is edible, we go to the processing plant. In the processing plant, we are going to have surplus foods. We're going to have industrial waste, and we're going to have byproducts. Then we go to retailer and consumer and consumption. We also going to have some leftovers that is considered waste, and of course the expired food. For the purpose of this presentation, I will cover some examples about surplus, industrial waste, and byproducts. Now, expired food and all that can be also a significant debate in terms of strategies, how to prevent it, or even how to have a use for those in those situations. For instance, the first one, we're going to talk about lactose surplus. So there is a constant movement and consumer behavior to increase the consumption of milk proteins. Part of that because of several health claims, control appetite, exercise recover, the typical diet if you want to lose weight, what it is high protein, low carbs, and milk proteins are a reliable source and a very good source of amino acids, essential amino acids. Not only that, milk proteins also have the very good functional properties. It can be used for emulsifier, to create gels, foams, and so on. The idea here is the more milk proteins we are producing, at the same time, lactose is staying behind because this is a filtration process in which lactose is separated, is removed, and then we ended up with in a situation that we have a surplus of lactose that we don't know what to do with that lactose. So if we see it in that way, the first generation or the first level of lactose use was just purified lactose. Take it from the cheese whey, dry it, or even filtrate it, dry it, and obtain purified lactose. And then there's what we can call the second level, in which you start with some chemical reactions or modifications to produce lactobionic acid, lactitol, and some other byproducts, even lactulose, which is a prebiotic. Some of the research I'm going to present today is about the third level or the third generation of uses of lactose, which is enzymatic hydrolysis followed by catalytic isomerization to produce tagatose, mostly tagatose, which is a rare carbohydrate. So why is the idea of using tagatose and allulose and those carbohydrates? If you pay attention to this table, in which is some of the components or carbohydrates, the relative sweetness and the caloric value. Sucrose, for instance, the relative sweetness is typically measured from 0 to 1 or 100%, and it provides a caloric value of 3.9 calories per gram. Lactose, for instance, is 10% sweet. The sweetness is 10% only compared to sucrose and the same calories. Fructose, glucose, and all that. For instance, tagatose here is 90% sweet, comparable to sucrose, and half of the calories of sucrose, for instance. And allulose is similar story. So those carbohydrates become very attractive to use it as sugar replacers. Now, traditionally, rare carbohydrates can be produced by enzymes. Now, the challenge with enzymes, it requires very long reaction times, control of pH, control the purity of the reactants, and the enzymes can be really expensive. So the approach here is to use heterogeneous catalysis. That is essentially an insoluble material that is impregnated with a metal that provide the catalytic activity. And by doing this work this process can work in conditions where the enzymes will not survive, like low pH, a broad range of temperatures, and it does not require purity in the substrates to react. So what I'm talking about here, we use a beta zeolite. What is a beta zeolite? Essentially, it's a rock. We remove the aluminum from that. We impregnated the metal that we wanted to react, and this is basically what we obtained in a very brief way. So, of course, we did a lot of the chemistry and physics characterizations about this catalysis by measuring the volumes, the pore, the functional groups presence in those materials to make sure the metal is present in those. And then we start doing the catalytic isomerization. So the first step, we use a two-step process in which we have lactose, for instance. We hydrolyze lactose with an enzyme. Nothing new about this one. The enzyme has been on the market for quite some time. So we ended up with 95%, close to 95% of hydrolysis of lactose. The next step, we perform the catalytic isomerization, and here is the interesting part. So lactulose, we have minimal amount of lactulose formed, but look at the amount of tagatose that has been formed. The yield of tagatose is comparable with what you typically found in the enzymatic process. Now, all this is exciting news, and it was very attractive. On the other side, if we think about it, if we pay attention to selectivity, the selectivity, what it is essentially is how selective is the entire process, or in this case, the catalysis, to favor the formation of tagatose over the rest. So the selectivity is relatively low here, around 50%, 40-something%. So what it means, we have the presence of several other compounds that were also formed. So that will give us the idea that, well, we can probably produce a syrup made of several carbohydrates. Think about this. Well, we try different matrices, lactose in solution, sweet weight permeate, acid weight permeate, and depends on the reaction conditions. We start with one carbohydrate, which is lactose, and we ended up with 1, 2, 3, 4, 5 carbohydrates. And the concentration of them depends on the reaction conditions and can be optimized. So the idea of this one, we take lactose and we convert it into a bunch of sweeteners that can be used all together. This is the idea behind this one, because if we really want to upcycle lactose, think about it the traditional way, and this is the concept of one-pot synthesis. In a very simple analogy, if the orange piece is the one that we want to produce, the piece of the puzzle, traditional synthesis is to purify, produce this one to the desirable compound and purify it so basically we get rid of the rest. And we just focus on that one. That is a traditional synthesis, and it can be done with tagatose, for instance, coming from lactose, but it requires several purification steps. And in this case, what I'm proposing here is one-pot synthesis in which we produce similar products or have similar functionality, and we use it together as a sweeteners, for instance. That is the concept of one-pot synthesis that will make a lot more attractive in terms of economics and in terms of potential scale up of this technology. This is the idea behind all this. We have weight permeate. After separating the proteins through filtration, we can do a one step, which is enzymatic hydrolysis, to basically split lactose into glucose and galactose, isomerize that mix, separate the catalysis on one side, and reuse the catalysis and obtain a sweetening syrup that can be used in many different food products with minimal purification. Here are some examples of chemical reactions that you can go or you can follow in terms of we want to upcycling lactose. And remember, what is the concept behind upcycling? Upgrade, and reuse. So if we think about lactose here right in the middle, there are many reactions that we can follow to form sweeteners, prebiotics, lactobenic acid, for instance, and so many other sugar alcohols. There are many ways many chemical paths that we can follow to upcycling lactose, for instance, in this case. The second example I'm going to provide you is a byproduct, and these are phospholipids. Here, for instance, we talk about whole milk, and the baby blue color represent the main product, can be cheese, whey protein concentrate, butter, sour cream, or anhydrous milk fat. And there is the main byproduct, and depends on the final product, contains, for instance, beta serum contains a significant amount of phospholipids, buttermilk as well, or whey protein phospholipid concentrate. And the reason of all this, the idea to recover and reuse those phospholipids, it has to do with health benefits. I will not go into the details about the health benefits of phospholipids, specifically those coming from dairy. That's not my expertise. I'm an engineer, and I like to destroy stuff, and I like to build that, not really understanding the health behind that. But there is a reason why, there is a motivation right there talking about the use of those phospholipids, and depends on the concentration. But the phospholipids are hard to separate because of the chemical composition. So in this case, we use a technology called switchable solvents. What it is a CO2 responsive species. It's a tertiary amine that in the presence of tertiary amine that can dissolve fat, and then in the presence of CO2, it switches into a salt that is water soluble. So a simple illustration here is this situation in which we have the solvent, the water, and then we can switch the ability of the solvent, and we can be hydrophilic, or we can extract and separate it by just bubbling in or removing the CO2 from the environment. So it's an illustration what we did with dairy phospholipids. We use the byproduct, we combine with the tertiary amine of the switchable solvent. And then after some times of extraction, we added CO2 and water to maintain the stoichiometry of the reaction. We separate the lipids from the water and salt. We add the hexane just to separate the lipid portion. And then we obtain we use different solvents to purify the phospholipids and the amine. We can switch it back to, the salt. We can switch them back to amine and can be used. These are the steps. Some pictures, and this layer represent the phospholipids. So by doing this technology, we actually separated. We tested different materials: beta serum, freeze dried, buttermilk, and this technology works very well in wet matrices, which is very positive because the total phospholipid recovery here, if we consider buttermilk, we were able to obtain 95% of recovery of those phospholipids in wet matrices. What it means, we don't have to dry the samples or the byproduct to improve the extraction. We also spend significant time on the mechanism, the potential mechanism of how this one works. And it have to do with the charges. It have to do with the particle size. So essentially, we stain the phospholipids in those matrices and start taking microstructure images and see how the phospholipids start to fractionate and separate from that. We spent a little bit of time on this one. So this is an illustration in which what is so attractive about dairy phospholipids is the unique combination. Probably you heard about it, how the membrane in milk works. It has a bilayer of phospholipids, and the phospholipids that are in the intracellular membrane are the ones that are more desirable in terms of the health benefits. And in this case, if we use the switchable solvent extraction, PI and PS, right here, PI and PS are the one that we obtain the highest concentration compared to the other extraction methods. Part of that because the switchable solvents break down the structure of the matrix, as indicated here in the microstructures, and release the phospholipids that are inside in the second layer of the membrane. So similarly, we use a spent coffee ground. This was inspired by a Colombian student that I have in my lab. He was really into the coffee. So spent coffee ground is after we brew the coffee, that is the material. It contains the total lipids until perhaps up to 11%, dietary fiber, there's chlorogenic acids of phenolic compounds and caffeine. So the idea, there is plenty of research try to separate this fraction, the lipid, the carbohydrate fraction, and the phenolic fraction. So in this case, we use the same technology, switchable solvents. We obtain a spent coffee ground from the university cafeteria. We combine it with the switchable solvent, and you can clearly see here the lipid phase separated from the matrix. At one point, once we start playing with the switch back of the solvent, we obtain the number 3 here, which is the dietary fiber. And then we keep doing in the separation, we obtain the phenolic compounds and the lipids from this from spent coffee ground. And the attractive about this one is we didn't have to go to distillation and using other solvents. So the carbohydrate fraction we characterize in terms of the total dietary fiber. It depends on the reaction conditions. We can get a little bit higher, a little bit lower, but this is just part of the characterization of the material. The water-soluble fraction of the phenolic compounds, we get a significant amount of chlorogenic acids, total chlorogenic acids, and we also measure the individual chlorogenic acids. And this is the attractive part. And this is something that we have to keep in mind when we work with this technology. The lipid fraction, which is very evident in this picture, we obtain higher values. We obtain really high values. So that was basically a red flag because the way we measure phospholipids, or lipids in general, here is through gravimetrical methods. So if the amine, the whole fundamental of this technology is based on the conversion going from the tertiary amine to the salt and to the salt to the amine back and forth. But if the conversion is incomplete, we'll start to consider amine as a lipid. So we send samples to external labs, and we ended up with we are over quantifying some of those lipids here due to an incomplete conversion of the amine. So that's something that if this technology start to develop into separating lipids from spent coffee ground, it's an important consideration to track down the changes in pH, track down how this simple conversion can be optimized, or at least knowing what is the maximum you can go back and forth with that reaction. The last example or the last topic I want to cover here is not really upcycling, but it's related to the energy and related to sustainability, and this is decarbonization of the food industry in general. So this is basically an illustration that the cost of energy versus the energy intensity of food, and the food industry is basically in the middle. Despite all that, it's been considered one of the carbon intensive industries in general, even though there is very low compared to industrial gases, chemical, steel, paper, and all that. But the fact that the food industry produce perishable materials that require constant production, it is considered one of the main contributors to greenhouse gas emission and all that. So the idea is to how we can reduce the dependence on carbon or decarbonization of this technology. In this case, what I start doing in this one is I focus on evaporation. Why evaporation? Because evaporation is one of the most intensive in terms of energy, and especially for the production of protein powders. Regardless of the source, whether it's plant-based or dairy-based, those proteins need to be evaporated. And so far, the most suitable way to evaporate food is through falling field evaporators, in which you have a tube, you create a thin film to the evaporator, the product you want to evaporate from a thin film, you put it in contact with the external side of the tube with the steam, and that's how the evaporation occurs. The idea here is to use guided ultrasound, which is different from the traditional ultrasound.
We can't hear you, Sergio. Hello? Can you hear Sergio?
No.
Okay.
No.
Something went wrong with your... I think it's your headphones, the problem. They got like disconnected or something. We can't hear you at all. No.
You hear me now?
Yes, now we can.
All right.
Sorry about that.
So let me go back into this one right here.
There, thanks. And change. Yeah.
Oh, sorry, I stopped the sharing the screen. Let it go again. All right.
There it is. Thanks.
I was talking about here the guided ultrasound. So essentially here, the main idea is to apply the energy, but with depends on the frequency and the angles, those waves can be guided through a specific geometry. So in this case, what I'm talking about here, the guided ultrasound depends on the time, frequency, and space. So that creates a new challenge. So in this idea, for instance, this is an illustration of the frequency and the application of the ultrasound domain, in which most of the food applications are right here, low frequency, high power. And that is a typical ultrasound we can use for emulsification, for break cells, kill bacteria, and all that. So then if we move higher in the spectrum of
frequencies and less power, we can end up in a situation like acoustics, microscopy, medical devices, but the guided waves is right here. Still, you will find some cavitation effects, but it's less power than the traditional ultrasound. This idea has been applied for its non-destructive testing of pipes and structures in civil engineer, so they can guide the waves through this one, collect the signal, and identify cracks or defects. Now, how is supposed to do this one in evaporation? So we did some preliminary trials in which we have a stainless steel pipe in a certain inclination. We ran it a sucrose solution to create a thin film. We applied the guided ultrasound waves, and we were able to evaporate a lot more efficient the solution without using the steam yet. So now this is preliminary work. What I'm trying to accomplish into this one is moving into the direction of actually applying this one into a larger scale. So what it requires a lot of modeling in terms of the pipes, how the waves can travel to a specific geometry, to a specific material. In this case, could be a stainless steel with a given thickness. And of course, once we are able to know how those waves travel to a pipe, we can start measuring the cavitation created by the guiding waves into this one. So combine these two, it can potentially reduce the use of energy of the carbon intensity of evaporation. This is in collaboration with a colleague of mine from Arizona State University, who's a civil engineer who's helping me with the modeling of the waves. And I'm trying to build the evaporator in a pilot scale. Now, these are some of the examples of case studies in which we will see cases of upcycling. But I would like to comment on some points here. For instance, my key point of all this is we have a very confusing terminology that we need to address as a community. I see a lot of these buzzwords a lot of the time, like circularity, sustainable, carbon-friendly, all the kind of, that it doesn't really help the debate. We, as a scientist, we have to come up with common terminology that we can use to what we are talking about circular, what we're talking about upcycling foods, and what are the limitations and applications of all this. Now, based on this one, I can make the case that we have to, we have the opportunity to upcycling foods, but we have to consider a transdisciplinary approach, using different fields that allow us to, again, what is the concept? Upgrade and reuse either materials, can be waste, can be byproducts, can be surplus, and so on. This is another one. The third point that I want to illustrate here is the balance between a scale up and a scale down. There is some arguments that not everything needs to be scale up, and in fact, some industrial operations probably needs to scale down. So we need to find the right balance between the scale down and the scale up. And what I mean by that, if you're working in a technology, the typical question you're always going to get is how scalable it is. I understand the concept, but sometimes it's not necessarily needs to be, we don't have to scale everything, scale up. My fourth point, and this is significant to me. What I'm trying to say here is we all want to have the transformational idea that's going to change the world, but that will never occur unless we have incremental steps. Incremental ideas eventually will lead to more transformative ideas. But if we go directly to the transformation, we're going to miss some of the fundamentals and end up with situations that we even confuse even more what we're talking about. And this is my final slide. This is how I look at the use of upcycling in foods. Use a three-plane diagram from the National Science Foundation. So essentially here is where we see food technology, or where we are as a food scientist, the core fundamentals, the basic principles, how we can use this one to apply research to solve problems that are relevant to the society. What I mean by that, for instance, sustainability, social responsibility, obesity, food waste, so on. With the idea, and don't forget about these points, we need to develop science-based solutions. And nowadays it's becoming very challenging because you find it through social media, everybody knows about everything. And why my point in this one is we need to develop science-based solutions. The other one is we need to develop our talent, the next generation of scientists that can work in a transdisciplinary environment. And of course, we have to engage the citizens around the world in these topics as opposed to just watching TikTok or something like that. And that will be my last slide, and I will open up for questions.
Thank you so much, Sergio, for this exciting and very interesting talk. Please, anyone with questions, you can either write them on the chat, as I mentioned before, or ask them directly to our speaker.
I cannot hear you. Let me see what I'm doing here with all this. Can you repeat that question or the comment?
No, that I'm asking for questions from the audience, so no worries.
Hi, my name is Celia.
Okay.
I have many questions, but one question is how we can involve in the solutions about for ultrasonic technology. For example, that for me is interesting. How expensive is to scale up, yeah. Another thing, what companies I can find or research in Mexico about this kind of technology? Thank you.
Well, traditional ultrasound, and I call it traditional ultrasound, but basically it's a power ultrasound, is the one that you use the horn and apply a frequency and the power goes localized. That one is, the scale up of that one is a challenge because it's localized. So you probably need to have several type of horns that provide the same benefit. Now, as I say, not everything needs to be a scale up. There should be maybe some unique applications that targeting a particular market. Now, in terms of what you can find companies in Mexico, I'm not really familiar with that, but I mean, with the internet, you can start looking for companies and start sending emails or even calls to see what companies can offer you some kind of services. Now, to add a little bit more about your questions, what I'm using right now is guided ultrasound, which is different in that sense, in the sense of you can guide those waves to a given geometry. Now, it hasn't been applied in foods yet, and we have a long way to go in terms of fundamental understanding of how guided waves can benefit food industry.
I mean, there's another question. Do you think the guided ultrasound can be better than freeze dyeing?
Can you repeat the last part? I couldn't hear you.
Freeze dyeing.
Freeze drying?
Yeah.
Oh, it depends. If I will say conceptually, yes. Now, that goes to the challenge how you keep in mind that basically what we're doing here is applying the acoustic energy into a geometry. And then we can find a way that those waves can travel or release the energy to evaporate, to cleaning, for crystallization, for freezing, and perhaps maybe for drying as well.
Thank you.
Thanks, Sergio. We have another question in the chat. What is the possibility of lactose recovery from whey waste obtained after coagulating milk protein?
So what is the possibility of recovering lactose? It's really how actually it's been recovered when once, let's take an example of making cheese. You coagulate the proteins and then you obtain the cheese whey. That one can be filtrated to microfiltration, nanofiltration, and then you obtain what is called whey permeate that contains lactose, minerals, and some fat. That is the lactose that I'm using to convert it into sweeteners. Yeah, it is possible to recover lactose after coagulation.
Thanks. Another question from the audience? Ricardo,
Hello.
go ahead. Oh, sorry. Let's follow the order. Ricardo, you can go ahead, and then, I don't know, Ana, please, after Ricardo.
Hi, Doctor. Just a quick question about regarding the modeling. What modeling approach are you using for the ultrasound treatment?
The details of the model approach, we just started working on that. I will need to consult with my collaborator. She's the one who is working on the. But what he's doing is basically model the velocity of the waves into a given geometry. It can be just a pipe, it can be an elbow, it can be different geometries.
So it is time dependent or independent?
Yeah, it is time dependent. It depends on time, frequency, and power.
Thank you.
Thanks, Ricardo. Ana?
Hello, Sergio. Thank you for this topic today. Hi. This is great. I actually work for DFA, and we do have a lot of waste streams that you kind of touched on today. For one, we produce a product making milk permeate, and we have permeate or a product similar to lactose as a byproduct. I was kind of curious, how far along is this idea to create this syrup? Because it is exciting to think about producing it into another food product other than milk permeate powder, because that's realistically what it's made for, or dumped, because there's not a whole lot of streams. If we don't have a dryer nearby, it is going to go to garbage. So that is unfortunate to see and hear, but that's the realistic truth of what happens to that byproduct, because it is a very low cost product. So that is my first question of how far along is that in idea, or what could I do to help that along in that process?
Well, firstly, good to hear from you, Ana. Just for everybody else to know, Ana was one of my students in South Dakota State University, one of the undergrads at that time. So now, to answer your question about how far we are, the part of the fundamental has been the application side of how you convert it using catalysis has been proven. Not just for lactose, has been proven for other matrices, biomass, and other stuff like that. Now, what is the biggest limitation right now? There is no commercial catalysis yet. You basically have to make it in-house. And that is a big limitation, because you made it in-house, what it means, you will have a lot of inconsistency. One day you will do it great, or other company will do differently. Now, perhaps at one point, we don't have to use that catalysis that I use. We can be another catalysis that are commercially available that probably gets a lot more robust idea. But my view on this one is a simple, well, not simple, but it's a chemical reaction. I mean, talking about a carbohydrate, a disaccharide that can potentially convert it into many other carbohydrates could be a reality. Depends on the availability of the catalysis. And my view on this one is, and it gets very personal here, because that's one of my research areas. So I get very passionate about talking about the using of catalysis into converting lactose into sweeteners. I will say this is possible. Now, how far? That all depends on the commercially available catalysis. But it was the same topic years ago when we're talking about the other chemical compounds. For instance, we think about it, sugar alcohols. They are produced to catalysis as well. Some years ago, there was the idea, no, we don't have any commercial catalysis, and now it's a commercial reality, industrial reality, the production of sugar alcohols.
That's great to hear. I would love to hear more about it, just because this is a big issue that I see, and I would love to have other options for our products as well. I'm also interested in the guided ultrasound, I guess, as a comment to learn more about it. And then you didn't talk about it just because it's not food, but a big byproduct, I would say massive byproduct from dairy facilities is solids. Solids is a major issue. I have found that facilities tend to send it to landfill, which is at the bottom of your pyramid. That's what we normally do unless we have another area to put it in, such as land application or composting, which is, if there was another idea of what to do with these great protein-rich sludge that we call it, that would be awesome. Because I mean, it's a major financial loss for companies, but it's a very normal loss, because that's what you have. You have solids that go to landfill or land application if you're lucky. So anyway, thank you for this topic today.
Yeah.
I appreciate it.
Thank you for your question. Yeah, talking about those salts, part of that is we have to change some point our mindset. That is the cost of doing business. We have waste all the time. Yeah, we are going to have always waste, but we change the mindset that we can reuse to some extent those waste, to maybe those salts have a potential use for some other products, but it is always we're going to have waste. And I didn't cover in this presentation. I've been working for the past few years on ice cream waste. And that is another big issue talking about the ice cream waste. It's a lot of fat, it's a lot of protein. And as you mentioned, it goes to landfill. And that is a shame because it's a valuable material that we can reuse.
Thanks, Anne. One last question from the audience.
As a small company, how can you advise me to involve in upcycling process little by little?
I'm more than happy to provide any comment that I can or any help I can give you. If you need it, I can share my email and we can talk about it. Because the way I look at it is individual case, because volumes matters. Where you produce the waste and where you can obtain the material matters a lot, because it depends on volume, pH, composition, so on, and depends on the right technology needs to be used as well. So my general view in with dealing with this topic and interacting with industry is we need to find solutions that are practical, but at the same time, we need to work on those solutions that require more research, that are still under development, like switchable solving, for instance, still a lot of questions, or the guided ultrasound. At this point, I have more questions than answers. But if we just put all the emphasis in the application side, we are going to miss the development of potential solutions. So my view on this one is we have to find a balance. Yes, the development, the fundamental science is fantastic, but at the same time, we need to find the practical application that is science-based, and it can solve some of, or at least mitigate some of these problems.
Thank you.
Well, thanks, Sergio, for this talk, and thank you, everybody, for being here with us today. And please keep tuned and check our website for the following webinar. And again, Sergio, thank you so much for the time and the knowledge shared with us today.
All right, my pleasure.
Bye-bye.